notice is that your green sheet, which is what you're going to be using on this year's AP exam, does not have de Broglie on it. Okay? But this would not be a formula that anybody would ever expect you to memorize. That would be silly. Okay? So what that tells me is either you're going to have a problem where they give you the formula, or more likely they're just going to ask you conceptual questions about it. Does that make sense? Okay, so I don't want anybody to get too bogged down, but what I wanted you to see, the really reason why I wanted to talk about de Broglie is this. Do you know how lots of people, Bohr, I think was the first one, who gave us the idea of energy levels, right? And let me ask you this. Can we have any old energy?
No.
We only can have very specific energies, right? What do they call that? They used a Q word.
Levels.
It was like it was quantized amount of energy, or a certain quanta of energy. Do you remember hearing that at any time?
Yes.
Okay, so one thing that's very cool is de Broglie either helped get there or validated it, because I want to show you something. In physics, if you have two waves that kind of go on top of each other, what happens? What's that called? Interference? And what kind of interference is it? Constructive or destructive. And so if it's destructive interference, does it kind of obliterate each other in a sense? Yeah. Okay. So what's very cool is you think about the problems that I had you do. Okay. So you think about these problems where, yes, we started talking about a car, but then we moved to an electron. An electron has a very, very small mass. And so what kind of wave, are we going to be able to notice the wavelength? Detect it? Yeah, because if you look at the formula for de Broglie, this would be something you should be able to do. De Broglie is Planck's constant over mass times velocity. If you have a really small mass and it's in the denominator, will you have a wavelength that's big enough to detect? Yes. Okay? Guys, look at the relationship. Mass is in the denominator. So if you have a very small denominator, what does that do to your overall number? It makes it big. Okay? Whereas the car has a big mass. So if we have a big mass in the denominator, what does that make your wavelength like? Really, really small. Okay? All right? So that's the idea. Okay? So really, de Broglie's idea was really on the order of electrons and stuff. I just wanted you to kind of see the contrast. Now, if you were to take an electron with its mass and with its speed, now, really, electrons travel way faster than 60 miles an hour. This is more like what it's going to travel at, okay? If you were to calculate this wavelength, what's cool is this. If you were to fit this wavelength around a sphere, okay? Now, I was trying to make it match up perfectly. Can you all pretend that that matched up perfectly?
No.
Okay, now you can. Okay, I fixed it. All right, so that wavelength, only if the energy, or we're representing the energy with the diameter, only if the diameter is perfect will the waves not have any interference. Does that make sense? They'll match up perfectly. If I were to try and make it just a little bit bigger, then who knows, maybe when they kind of come together it goes like that. Okay, that's not good. Okay, that's going to have some destructive interference, and that's going to kind of muck things up. So what's really kind of cool, because I remember I used to go, why the heck do we care about de Broglie? How is that really helping us with atomic structure? Part of it is this. It kind of validates or lets us see what is that optimal energy level. Does that make sense? Okay, so that's part of why we talk about de Broglie. All right.